All right, we're continuing with Chapter 3 of the Calculus textbook. In this video, we're going to go through Section 3.9 on related rates. Now, we're skipping Section 3.8, exponential growth and decay. This we go over in great detail in differential equations. So in the differential equations playlist, we're going to get into exponential growth. All this is talking about is, so when you're modeling something with an exponential, we talked about in Section 3.7 how the population function, the population doubled every hour. And so you modeled it with like a constant. It was a function is equal to a constant times 2 to the t power, right? That's an exponential. That's exponential growth. It does like this, like a 2 to the positive t. But if you have exponential decay, it's like a base to the negative x or t. So it does like this. And when you think about the differential equation for exponential growth or decay, and if you don't know what differential equation means, don't worry about it. But the differential equation for any exponential, any base exponential, so e to the whatever power, 2 to the whatever power, you'll have, so dy dt, the derivative is a function of the function itself. And more generally, you can put a constant here. And so, well, how is that related to exponentials? Well, think about it. So when we had like 2 to the t power, what's the derivative of 2 to the t power? It's, you just put 2 to the t and then natural log of 2, right? So so the derivative is, it contains the function itself. With like e to the t, the derivative is just e to the t because the natural log of e is 1. And what will happen is this k here is going to come here, right? In the differential equation, the k is going to be in the exponent of the exponential. So that's just giving you a general idea of exponential growth. Again, we're going to go into this in detail in differential equations. Okay, related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and their rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. So what this is saying is a typical application of related rates. It's not necessarily the only application, but you've got this system and you can easily or more easily measure the rate of change of one quantity. So what can you easily measure? Like pressures, volumes. So you've got this rate of change of a quantity that you can measure, but you want to find the rate of change of another quantity that's harder to measure, or maybe it's even impossible to measure. And you're going to do that by relating the rate of change of the quantity you can measure with the rate of change of the quantity you're looking to find with like an equation. Okay, now these types of problems in calculus are called related rates problems. And every problem we're going to look at here, they're all rates in the sense that it's something changing with respect to time. But just keep in mind that you can apply this generally. As long as you have two quantities that are changing with respect to the same independent variable. So like we have a cost function, right? You have a quantity that's changing with respect to the number of units manufactured. Well, if there's another quantity that also changes with respect to the number of units manufactured, then those rates, you can call it, I guess it's not a rate anymore, it's not related to time. Those are potentially related if they're contained in the same equation. Okay? So we're going to go through the example problems here. And I'm going to try and point out what I remember always confused me about these types of problems when I first started doing them. So, all right, air is being pumped into a spherical balloon. So it's a spherical balloon. We know the volume of a sphere, so that its volume increases at a rate of 100 cubic centimeters per second, right? And so this is more easily measured. You can get this quantity. You can measure this quantity. Maybe you have a volume measurement device. It takes 50 volume measurements per second, 100 measurements per second. You get this plot of data points, and you do a curve fit and you can find its derivative. So you know the rate of change of the volume per second. And it sounds like it's saying here that this rate is constant. So they get the data points, and it's like all the data points are making up a clean line, right? A line with this clean line with the same slope. How fast is the radius of the balloon increasing when the diameter is 50 centimeters, right? So we know the rate of increase of the volume, but we want to know, well, how fast is the radius of the balloon increasing? You can't really, it's hard to measure the radius precisely. Well, these are related. These are both, the volume is a function of time. The diameter is a function of time. And they're related, how? By the formula for the volume of a sphere. Okay, so if we come here, this is the formula for the volume of the sphere. This is that equation that relates the two variables. 4/3 pi r cubed. So the first thing you do is you get your formula that relates the two variables. In a lot of cases, it's going to be like a geometric formula. But it could be anything. If it was the cost function problem, it could be anything. An equation that relates the two variables. Then what you're going to do is you're going to differentiate both sides of the equation with respect to the main independent variable. These are changing with respect to time. That's how these quantities are related. They're changing with respect to time. The volume is changing with respect to time. The radius is changing with respect to time. Pi is a constant. 4/3 is a constant. You just have v sub t and r sub t. And so that's when they're talking about using the chain rule. Why do we need to use the chain rule? Because we have v as a function of r as a function of t. We're going to need to say, okay, dv dt, so that's the left side as a function of time to differentiate with respect to time. And then dv dr dr dt, right? Like how do you take the derivative of r 4/3 pi r cubed with respect to time? It's 4 pi r squared dr dt. That's the chain rule. It's you have the derivative of 4/3 pi something cubed. What's the derivative of that? Well, you bring down the 3. That's 4 times pi times that something squared times the derivative of that something, dr dt. Okay, so this is if you're uncomfortable with the chain rule, it's going to be hard to do related rate problems, and not just the chain rule, but using it to differentiate general equations. So we learned this technique in implicit differentiation. So if you need to, go watch the video on the chain rule, or the multiple videos where we work practice problems, we go through the textbook, and also go watch the video in example problem videos. So all the videos on implicit differentiation, where we differentiate entire equations and have to use the chain rule. Like we do, like, you know, the derivative of y squared is 2y dy dx, right? That's the chain rule. Okay, so we took the derivative of this equation. What do we do next? We solve for what we're looking for. We're looking for dr dt, right? That's the whole point of this. We're trying to find this rate of this quantity, this rate of change of this quantity that's hard to measure. So we solve for it. Great. Now, once you get to this point, this is what would trip me up in some problems. So, okay, how do we find dr dt? We need to substitute values in here. We have 1 over 4 pi, that's constants. Okay, we have r squared dv dt. Well, we know dv dt. That's what we're given at the start of the problem. That's 100 cubic centimeters per second. Now, this problem's not so much of a challenge, but sometimes I found it confusing when to make the given rate of change negative and when to make it positive. This problem is not as much of a challenge, but in upcoming examples, I'll show you how it can be confusing. To get around not messing this up, what you need to remember is that it's all about the equation you use to relate the two variables. That's what you're focusing on. Go to your equation that you're using to relate the two variables. Okay, now, well, actually, in this problem, it tells you the volume is increasing. So we know that dv dt is going to be positive. So this is not that difficult here. But you'll see in upcoming problems that you need to really, they don't tell you explicitly how a quantity is changing. You're just supposed to figure that out based on the nature of the problem. And to do that, you're going to need to go to you need to focus in, dial in on the equation that relates to variables. So here it just tells us that we know that the volume is increasing with time at this point when the radius or the diameter is 50 centimeters. So we're going to put dV dt is going to be 100, and then R is going to be 50. Now, how is R a part of this? Because that's what the rate of change of R with respect to time is a function of R itself. It depends on the R value you're at. It's more complexity involved. The rate of change of R with respect to time is a function of 1 over R squared. It depends on the R value you're at, right? It depends on the R value you're at, and it also depends on the rate of change of the volume at that time. Well, this is always constant. dV dt is always constant, but in some, maybe it's not. Maybe in some cases it's not. So that's what they do. They plug in 100 for dV dt, positive 100 because it's increasing, and then they plug in 25. Now, we know that dr dt is going to be positive because if the volume is increasing, we can intuitively see, if we come to the formula, if the volume is increasing, that means the radius is increasing. But even if it was confusing, even if we weren't sure what dr dt was doing, as long as we get our inputs right, the signs of our inputs right, then the final answer will tell us what the rate we're looking for is doing. Okay, so the radius, if the volume is increasing at 100 cubic centimeters per second, and make sure your units are all consistent when you do this. If the volume is increasing at 100 cubic centimeters per second because of how much air we're pumping into the balloon, it's a spherical balloon, then at the moment when the radius of the balloon is 50 centimeters, they put 25 for the radius, or when the diameter is 50 centimeters, that's why they put 25 for the radius. The radius of the balloon is increasing at a rate of 1 over 25 pi centimeters per second. Centimeters per second. Okay, example 2. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so as far as, what we talked about in the opening paragraph, this is probably not that common of a situation. This is just more to practice doing related rates, because if you can measure this distance change, then why couldn't you just measure this distance change? And then why would you even be doing this? So this is just to practice the concept of related rates. This volume problem seemed a little more realistic. You can measure volumes, pressures, right? It's harder to measure an exact radius. Here, I'm not sure, what kind of application this would come into, but okay. So we've got the rate of change of something that we know. We know it says that the ladder slides away from the wall. It's sliding in this direction at a rate of 1 foot per second. That's how fast this X is changing. So consequently, this is sliding down the wall. This point is sliding down the wall. How fast is this sliding down the wall? The nature of these problems is that the quantity the rate of change of the quantity and the rate of change of another quantity are related because of the nature of the problem, right? These are related because they're all part of this ladder. These are part of the triangle made by this ladder. Okay, so what's the first thing you do in a related rates problem? Well, you read the problem and get a feel for what's going on. But then the first thing you're going to look for is, okay, so identify what's the rate, read the problem and identify what's the rate I know and what's the rate I'm looking for. Then think about, okay, how are these two quantities related, right? I guess you can think how are the rates related, but how are the two variables related? What's an equation I can use to relate them? And then you write that equation. And so here, this is a right triangle. And no matter what position the ladder's in, this is always going to be a right triangle, assuming the ladder is always in contact with the wall and the ground. So x squared plus y squared is equal to 100. Now, what would trip me up, how I would mess this up is I would like want to do a coordinate system. And I would, it was, so here it actually doesn't mess up, but like, so I would say, okay, here's the origin of my coordinate system. That's X. That's Y. If something is moving in the positive X direction, it's positive. If it's moving in the negative Y direction, it's negative. And here it actually works out because this is moving in negative Y and this is moving in positive X, and that actually works out correct. But this would screw me up a lot of times because what I should have been doing was, okay, well, before I talk about this, the next step is you have the formula that relates your two quantities, and the two quantities are functions of the same independent variable, right? That's how they're related. X of t, x is a function of t, y is a function of t. Differentiate both sides with respect to t. Use the chain rule, right? This is just 2x dx dt, 2y dy dt is equal to 0. Okay, solve for, we're looking for dy dt. Boom, we got in here. Now, the challenging part I found is plugging in the correct signs for at least the rates of change, and even maybe the variables themselves. So think about how you plug in the correct signs. Focus on the equation that relates to variables. It's all about that equation. Right here, we've got the Pythagorean theorem for a right triangle. That's what this is. So we're looking at a triangle. It's always a right triangle, and it's just the type of right triangle is changing, but it's always a right triangle. So we've started here, and as according to this equation, y is decreasing. This side length is getting smaller. This side length is getting larger. Now, when I use a coordinate system, an xy coordinate system like this, that turns out to be the case regardless, right? You're going in the negative y direction and the positive x direction. This point is going in the negative y. This point is going in positive x. So it works out. But there were other problems I would come into where it wouldn't work out that way. Where I would do the problem, I'd use the sign convention, and it would come out wrong. And what I had to do was realize, okay, I have something in I'm using a kind of a geometry formula, right? This is like a geometry formula to relate the variables. What's the geometry of this? How is when I draw like the whole shape of this on the page, how are the lengths changing, the shape lengths changing? That's what it's about. Okay, so what they're going to do is they're going to plug in dx dt. It tells us that the bottom of the ladder is sliding away from the wall in this direction. So this side length is getting larger. I'm saying side length because that's what this equation is about. This is the side length 1 squared plus side length 2 squared is equal to 100. So that's why I'm saying side length. This side length, well, it doesn't matter, but we expect to get a negative answer for dy dt. So dx dt, they plug in 1 here. And then x and y, just put the value for x, put the value for y at that point in time. So how can we solve for that? Okay, the ladder is 10 feet long. That doesn't change. We're solving for when the bottom of the ladder, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So x is 6. So we can solve for y, and we get x and y. Now, you can see how that's confusing as well, because if I'm using my coordinate system, again, it doesn't matter in this problem, but I'm tempted to put, oh, well, I've got a negative x here, right? I'm in the negative x direction. So I'm putting a negative for the x. Again, this problem, it doesn't matter, but for other problems, it would. But when you're thinking about it from your equation here, from a geometry problem, there's going to be no negatives. Your relations aren't going to have negatives. You're relating shapes geometrically. If you're using the Pythagorean theorem, if you're using sine, cosine, or tangent in a related rates problem, you're not going to have any negative values as far as like the lengths of some of the shape. Yeah, one of your rates might be negative because that length of the shape is decreasing. But you get what I'm saying? If this triangle if we did the problem like this. Right? And so this was x, this was y, it's sliding this way, and this is coming up. Well, that's going in the positive y direction. This is going in the positive y direction. And y, when x is equal to 6, y is equal to -8. Right? Y is in the negative direction. I mean, maybe that works, because I guess, okay, if you get this same formula And dx dt is still positive. You get negative y here, so you end up getting positive 3/4 feet per second. So that does mean dy dt is moving in the positive. Per the solutions, like the solutions manual of this textbook, I wouldn't get the right answer. If you have a comment on this, then drop a comment. I mean, I guess maybe you could set it up this way, but as far as the solutions manual of this textbook, these professional mathematicians, you don't do it that way. You do it. Doing it this way is you're going to get the wrong answer. We would get a positive dy dt. Like here for this problem, you would want to get a like even if the triangle was upside down, dy dt. If this is moving to the right and both ends of the ladder are stuck to the wall, dy dt is getting more negative. This length is decreasing. But you know, the more I look at this, I guess you could set it up that way, right? Because what if this wasn't a wall here? What if like this was just like a linkage, and so this ladder could go anywhere up this vertical wall? Then you would have y be in the negative direction. Y is dy dt is increasing. It looks like it would work just fine. But then you would have like, you know, the Pythagorean theorem, once this would switch from, this ladder would go from horizontal to vertical, you would have like I guess you would have a different Pythagorean theorem. You get what I'm saying? Like it's all about this equation that relates the side lengths. So I mean, you can look into this yourself, work a bunch of related rates problems, see what you think, try it with different methods. But all the problems we're going to work here, we're doing it where we're looking at the nature of the equation that we use to relate the variables. Okay. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so they draw a sketch here. This inverted circular cone, this is the base radius, that's because it's an inverted cone, so this is the base, is 2 meters. The height is 4 meters. Water is being pumped in at 2 cubic meters per minute. So that's the rate that you know. You know the volume flow rate of what you're pumping in, right? Like you can have in a lab, you can have a flow meter. You can easily have flow meters that are measuring the exact flow. But to have like a height measurement meter or a radius measurement, that's harder. But you can use related rates to find the rate of increase of R or H. But they want us to find the rate of increase of H. So, okay, what's the formula that's going to relate the volume to the height? Well, the volume of a cone, 1/3 pi r squared H. Now, this is a little bit tricky because, okay, 1/3 pi, that's constant. We have our H, we want to find dH dt. We've got this r squared though. Is that constant? No. If the volume is changing, the r is this. It's the radius at the water level surface. If volume is increasing or decreasing, r is a function of time, just like h is a function of time. So, okay, I mean, do they give us the rate of change of the radius? Well, they're not going to give us that because that's hard to measure, right? How would they give us that? They couldn't give us dr dt. You can't measure that accurately, the radius of the surface, the water level surface. So when you're working a problem like this, like out of a textbook, or even in real life, you want to find out how you can relate the variables like this. Can we relate these geometrically, R and H? Yeah, they use similar triangles. If you remember from geometry how to work with similar triangles, this triangle and this triangle are similar. And so with similar triangles, what you say is 2 divided by 4, 2 divided by R is equal to, and you can do any other side you want. So 4 divided by H. Now solve for R. 4R is equal to 2H. R is equal to 1/2 H. And now we plug in 1/2 H for R. And now we've got the volume strictly as a function of the height. There we go. Take the derivative of the entire equation with respect to time using the chain rule, then solve for dH dt. And we get this here. So that we know the volume is increasing, so just put in this positive dV dt. And if we come back here, yeah, it gives us the water height. What is the rate of change of the height whenever the water is 3 meters deep, whenever h is 3? So we plug in h is equal to 3, and there we go. Units are meters per minute. That's the rate of change of the height. Okay, car A is traveling west at 50 miles an hour, and car B is traveling north at 60 miles an hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Yeah, so here we go. I think this type of problem would screw me up. So what I would do is I would put my XY coordinate system. Okay, so what it's looking for is the rate of the distance. How is the rate of the distance, the exact distance, the straight line distance between the two cars? How fast is that changing at a certain point in time? So we're looking for dz dt. We know that car A is traveling at 50 miles an hour in this direction. Car B is traveling at 60 miles an hour in this direction. So let's do this the way that I would do it in the beginning and see what happens. Okay, so again, we know the rate of change of this position of B and of A, but we want to find the rate of change of Z at a certain point in time. We can. What's the equation that relates those? The Pythagorean theorem. So if we come here, Z squared is X squared plus Y squared. Differentiate that entire equation with respect to time and solve for dz dt, and you get this. Okay, now, so what would I input with the way I used to do it? What would I input here? Well, I would say dy dt is positive 60, right? It's moving in the positive y direction at 60 miles an hour. And then car A is moving in the negative x direction at 50 miles an hour. So I would say that dx dt is negative 50, dy dt is positive 60, y is, so, okay, it's saying at the moment when car A is 0.3 miles and car B is 0.4 miles from the intersection. So at the moment when this x is equal to 0.3 and this y is equal to 0.4, but I would put positive 0.3 for x, right? Because it's positive here, and I would put negative 0.4 for y. So 0.3 and then negative 0.4. And then z, I would just I'd solve for z. They give z is 0.5, right? Just solve for z. Do 0.3 squared plus 0.4 squared is equal to z squared to get z, because z is also a function of dz dt, z itself, at that moment. So, okay. 0.5 times negative 50. No. 0.3 times negative 50 minus 0.4 times 60 divided by 0.5. And look, I get the same answer. So maybe you can do it that way. I don't know. Maybe my mind is clear now and I'm doing it right. Yeah, so I mean, you can try both ways. I mean, if try both methods, but the way that I had kind of changed to doing it was, so you got your formula that relates to two variables. Z squared is equal to x squared plus y squared, and you look at it like, what is that relation? It's a triangle, right? It's relating this triangle, this right triangle. So what is the side length doing here? It's decreasing. Dy dt is decreasing. And there's no such thing as a negative y when we're talking about side lengths of a triangle. A triangle can't have, a geometrical shape can't have a negative side length. And so you would say dx dt is negative, dy dt is negative, x, y, and z are positive, and that's what they plug into the formula. Positive 50, or no, negative 50, negative 60, and then just plug in x, y, and z at that moment, and you get negative 78, which means that makes sense, right? Because this length here is getting smaller as these two approach the intersection. Z is getting smaller. You would expect that to be negative. Okay, a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So here's the problem. The man we know is walking in this direction at 4 feet per second. We know the distance that this searchlight is from the wall, and the searchlight is tracking the man, is focusing on the man as he walks. So this angle is changing. We know the rate that the man is walking in this direction. How can we use that rate to find the rate that theta is changing with respect to time? That's the main independent variable, time. Well, how can we relate these two variables? Just using trigonometry. So not the Pythagorean theorem this time, but opposite over adjacent. X over 20 is equal to tangent theta. X is equal to 20 tangent theta. There's your relation. Now differentiate with respect to time. Use the chain rule, and then solve for the variable you're looking for, d theta dt. Here's that equation. Now we just need the hard part, in my opinion, plug in your known quantities with the correct signs. So the man is walking along the straight path. So the man is walking at 4 feet per second. Our equation that relates to two variables. This is a geometry equation. It's about this triangle here. The side length of this triangle, as far as our equation is concerned, this is getting bigger. dx dt is positive. So dx dt is going to be 4. That's going to be positive. Okay, what else do we have? Well, we have to solve for theta. It's going to give us, when the searchlight is located on the ground 20 feet, okay, when the man is 15 feet from the point. So when x is equal to 15, we can solve for theta and put that theta in here. And we're going to expect d theta. What do we expect d theta dt to be? Positive or negative? It's going to be positive, right? This is getting bigger. And it is positive. Yeah, 0.128 radians per second. Okay, now we're going to work a bunch of example problems so you can get a really, really good feel for this.